Hey, welcome to this recap video about cryptography and encryptions. I'm trying to be pretty fast here because that's pretty much a broad topic. So let's get started. We are going to cover three kinds of encryptions here. We are starting with hashing and then symmetric encryptions and then the so-called public key infrastructure. And after that we wrap up with digital certificates, digital signatures, and how HTTPS works. So let's see. Our first topic is hashing. That's quite simple. If you guys remember, this can be used, for example, for storing passwords in the database, or also it serves the basics for digital signatures. The general idea is that this is a one-way encoding. You can encode any kind of data. It becomes an encrypted text, right? But there is no way to decode it. And as crazy as it sounds, it actually works. So for example, how we can use that, we can, if you want to store a password in a database, and let's say you run an online service, your user enters the password, and you don't actually need to store the password in the database. You just hash it with this one-way encoding. You have some encrypted text. You store that text in the database, so you have no idea about the password. If the database gets hacked, the passwords will not escape because there's just some kind of a hash in there. And the next time the user comes in, you go and take the password. When it tries to authenticate, you encrypt it and just check if the hash, what you store, is in pair with the hash of what the user gave as an input for a password, right? And if they match, you know that's cool. So that's a good use case. And also, as you will see later, another good use case is hashing documents. So you have any kind of document and you just want to create kind of an ID of this document, you can do that because a very nice feature of hashes is that there are incredibly low chances that if you take any kind of data, let's say a document, and you take another data set, let's say another document, and you hash both, there is an extremely small chance that the two hashes are the same. So those chances are, just to have two document hash match, those two chances are less than, let's say, your house hit by a meteor 1,000 times in a row. It's really crazy low. So basically, it's they don't collide. Okay, so that's about hashing, pretty basic concept, and we checked some of the hashing algorithms. So one was here with R, for example, the so-called SHA 256. You can get to this by using the digest library. If I execute it, I can just say hello to a better hash, and I want to hash it. You see that my hash message looks like this. You also see that my hash message is 64 characters long, and the number of possible hashes with SHA 256 is around 10 at the power of 76. So that's just crazy low. So that's hashing. It will be extremely useful later. Our next concept is symmetric encryption. So symmetric encryption is, I believe, the intuitive idea of encryption. You have some kind of an encryption key. So let's say there is you and I. We exchange an encryption key, kind of a method how we encrypt and decrypt the message. And then I have my message. I will use it for encrypting. I will use the key or any kind of the method we agreed on for encrypting, send it over to you, and you can decrypt it using the inverse method, right? So one good idea here is the so-called Caesar method. what the Caesar method does is that it just shifts every character. So if you have a text, let's say hey, and you have a Caesar method with a Caesar shift of, let's say, one character, it means that for hey, this method will just shift all of the characters by one single characters. So from H, I will have Y, from E, I will have F, and then from Y, I have Z. And then I have this IFZ, that's what I send it over to you, right? You receive IFZ, and then you apply the Caesar method, but now the inverse Caesar method, just taking the -1 character shift, and you're back with hey. Okay, so that's extremely simple, but you get the point. You can come up with much more sophisticated algorithms like this, and they work very well. So let's see what's the problem with those. The biggest problem is that in order for us to exchange an encrypted message, we still need to meet in a protected place where no one sees us, and we need to exchange keys and methods, right? So we still need a safe place where you can go and just exchange the algorithm. And after that, we are all cool, but we need that place. So there is a quite novel concept. By novel, I mean, I think it started around the 60s or 70s. A mathematical concept which is now part of the encryption systems, and this is called the public key encryptions, or the public key infrastructure. Now, the public key infrastructure it's super interesting and follows a very, very different logic. It means that you have two keys. Let me just show this to you. So I will just come here. So you have two keys. Let's say here I am. So that's me, Zoltan. And I have two keys again. So I have something which is called the public key. I will say PU, the public key, and then I also have a private key. So not a simple key and a method like in Caesar, but two keys, public and private. And the idea, the mathematical idea behind the public infrastructure is that if I take a text and then I apply the public key, I encrypt this text with the public key, I get to some encrypted test, right? So I will say E here, and that's encrypted. And if you want to decode it or I want to decode it, I cannot use the public key for decoding it. It's just mathematically not possible, but I need to use the private key to decode it. And then I'm back to X. So that's a very interesting concept, because now you have two key pairs which are tied together, right? Public and private. And if you encode something with the public, you can decode it with the private. Usually this is the way how it goes. You encode with the public and you decode with the private. But in some cases you will see it also goes the way around. So encoding with the private and then decoding with the public. It really depends on the implementation if the private encode, public decode part is allowed or not to use. So that's the public key encryption, and usually how that works is that I go on and again I have the public, right? And I keep the public. So I can give this key to anyone, and I keep my private key protected, right? So that's protected, but the public is public. So if you want to send me an encrypted message, then you can just say So let's say you're Anna, and here I am. So you want to send me an encrypted message. What you can say is that, hey Zoltan, can you give me your public key? And I would say, sure, here is my public key. Then you take my public key, you have your message encoded with the public key. This will become the encrypted message, right? And then you send the encrypted message back to me. So I have E. And this encrypted message can only be decrypted by my private key. So I apply my private key to this encrypted message, and then I'm back to X, and I have X. Okay? So that's an amazing idea which very much disrupted the cryptographic world, and that's the public key encryption. Super cool. So let's see. When we have all of this, we are very much ready to come up with methods of going and creating digital signatures. This is how you do that. So here is a very simple example. You have some kind of a document. So let's say it's a text document. You want to digitally sign it. Your text document, usually what you do, you add a timestamp to the text document. So you say it's a time of signature. You can think about adding this time of signature is really just like, for example, if that's a text file, just adding a new line. If that's a Word document, then you would probably just somehow combine with some text of the signature, for example, of the document. And then what you would do is you would add your signature hash. So what's a signature hash? A signature hash would be taking the text document and the time of signature added and using your private key to encrypt it. So what you would do, let me just put it here. So here, you would take these two and you would use your private key. Whoops, sorry. This is not what I wanted to say. Let me rewind here. So you would go and just take the text document at the time of signature and just create a hash out of it. Okay, so we have the hash. And now what we want to do is that we use our private key to sign this hash. So let me have a bit of a more formula-driven display here. So I will say sign the encode the hash with my private key. And then what I would have is I have the text document, the time of signature added, and these two are now signed with my private key, right? Basically by having a signature hash which is signed by the private key. So if this is what I'm sending over to you, so what you can see is that you have a private key signed signature hash. You also have my public key because it's public, right? So you can use my public key to decrypt this text, and then you are back to the signature hash, and you can just go and hash the document and the time of signature added your own way. The hashing function is, that's a public thing. So you can actually put it here that you have SHE256. So this is what you're using for hashing. You can go and at your computer, you can rehash this and then just check if the hashes match. So your calculated hash and what you received. And if the hash is matched, you can also be sure that this message was hashed by the owner of this public key, right? because it was encrypted by a private key of that owner. So this is how digital signatures work. Now the only problem to solve is how would you go and make sure that you can be sure who is the owner of this public key. So if I can be sure that you are the one who owns this public key, the rest just follows. Then I know that the signature hash was signed by you because it can be, it was encoded by your private key, and then I can just check the validity of the document. So the problem, who owns this public key? And this comes to a completely new architecture of IT components in today's system, and these are digital certificates. So digital certificates, or it's also called sometimes a certificate chain, is a method with which you can ensure that someone is the owner of a certain public key. And let me explain you how that works in practice. So here is my public key. Let's keep this. Okay, so this is Zoltan's public key. Now, if I want to just go and somehow make sure that this public key represents my identity, what I can do, I can also add my name. So my name is Zoltan Todd, and I can also add my address, right? And any other information. And I can, of course, keep the public key, that's the central piece, and just somehow put it in a document. Okay, so this will be my digital certificate. And what I can do here is to have this digital certificate to sign by someone, digitally signed by someone who we all trust. And this can be, for example, a so-called certificate authority. Let's assume we have a certificate authority, and this certificate authority has a public key that we trust. We know that this public key is owned by certificate authority X. So they have an access pub. Okay, let me just put rather CA, so certificate authorities public key. So we will get back how we can make sure that the certificate authority is valid. But for now, let's assume we know it's valid. So we can just take this certificate authority, just go into an authorized room. Usually these are, if you want to have your own digital signature, authorized room, like physical rooms. When you go, take your ID and any other document, and you get a digital certificate created, and then the certificate authority that handles your business, they will go and just sign your digital certificate. So they will go and just digitally sign this digital certificate. So your digital certificate. Digitally sign means that they will hash it and encode it with the CA's private key, right? So anytime then you show this digital certificate to someone, they will know that that this is valid, because they can use the public keys of the certificate authority to check the digital signature on your certificate. And when the digital signature is checked, they can be sure that this public key is really yours. Okay? So now this is kind of solved. The only problem is how can we make sure that there are certificate authorities and that we know there are public keys? And the answer is, well, it's pretty easy, but perhaps somewhat surprising, is that there is a consensus in the world about the so-called root certificate authorities. These are the trusted root certificates. You have it both in Windows and Linux and OS X, and they should be more or less the same. And here are, for example, some of them. So you see, there are companies who are actually trusted worldwide. So for example, this is the at-rest external CA root. You see that here is, for example, their hash. So if you take a look at the certificate and you hash it, like the at-rest external CA certificate, and you get this hash, you can be sure that this certificate is valid and the public key you see there is valid, and then you can check any kind of a digital certificate which was signed by at-rest for validity, right? So it kind of creates a chain. So first, you have your OS, and your OS can validate the root CA. So here we check, for example, at-rest, and then let's assume that my certificate was signed by the at-rest certificate authority. Then based on that, I already know that the CA's public key is okay, and then I can use the CA's public key to validate my digital certificate. Okay, and if my digital certificate is validated, you know that my public key is okay. That's how it works. And as you can probably figure, there are these root CAs, but actually there are also different other certificate authorities. So you can set up your own certificate authorities. It's of course you need to comply to some regulations, and you need to start a business for that. But you can do that. So you can be an intermediate certificate authority. So this can be kind of a chain. So for example, I have at-rest, and when at-rest validates an intermediate CA, so I will say like int CA, and then my digital certificate can be signed by this intermediate CA, and it can validate my digital certificate, right? And this can go, as long as you want. So it's really a chain of certificates. Now this is how it works. So now we pretty much solved it. So we can hash documents, we can sign documents, and we can make sure that the signer's identity can be verified, because there is a global trust in each computer on the world for some of the root authorities. So that's how this goes. And let me see how we can put all of this together. So an HTTPS request. Now, let me say an HTTPS request in detail. What happens with an HTTPS request is that here are you, the client, and then there is a server, of course. You make a connection. This is a not encrypted connection. And what the server will do, the server will send you their public key, okay? And also the certificate. Well, public is part of the certificate, right? So the server sends you the certificate, and the client goes on and validates this certificate. So the client says, certificate okay. And then the client starts sending messages to the server, messages that are encrypted by the server's public key. So the client goes and just says messages which is encrypted by the server's public key to the server. And this is still not encrypted. So this is a not encrypted channel. So the messages are encrypted, right? But so far, nothing was encrypted, but now I'm sending a publicly encoded message to the server. So by not encrypted channel, I mean that, for example, that your Ethernet cable, it is not encrypted. The message is encrypted. Okay, so I send this message to the server, so we can communicate with the server now in a way that, what the client says, it can be decoded by the server's private key. So the client can tell the server that, hey, use this and this kind of symmetry coding. So I will say this is encoded again by the server's public key, so a secure server. So the server says, as if it said, hey, let's use the Caesar code and let's make the character shift to 3. And the server can say, okay. And at this point, client and server can forget about the certificates, and the client can just go and communicate with a symmetric encryption, client and server both ways, with using some symmetric coding they agreed on. And this one is usually simple and computational, not too expensive. So compared of the client and the server exchanging public keys and then just sending messages here and there. Okay, so HTTPS starts with a private public key exchange, a certificate check, and then in a secret channel, client and server can go and simply just exchange a symmetric method, a symmetric key, and then just continue the communication like that. And you can also see that in practice. So let me show you a quick practical example. Here we go. Here is CEU.edu, right? Here you see this little lock. If you click the URL, double click, you see it's HTTPS, so that's a secure channel. And here it says connection is secure. Here is the certificate, you see. So the certificate is valid. It's a CEU certificate. You see that it's a Hungarian entity. And the certificate authority is DigiCert Inc. And you see, for example, the signature of this certificate, which is, of course, encrypted by the DigiCert's public key. Yeah, and that's it. And you see a lot of things. Oh, here it is actually, sorry. Here is the actual SHA fingerprint, so the hash. And then what you can check is then, at this point, you can go and just check out the DigiCert's certificate. You see, this is the intermediate certificate authority. You see that this is DigiCert, it's a US entity. Here is the fingerprint of this document. And then you can go, and the root authority is actually another DigiCert business as DigiCert's global root CA. And you see, this is signed by this fingerprint, and you see it starts with 43 and then 48. So this is a signature, and you can go to, let's say, your Mac, and let's just check 43, 48 it was, right? Yeah, there you go. So here you can see right away that this is stored in your computer, and also in Windows you will see the same. So this is stored on Windows, so this is a trusted entity. So that's a recap of encryption and digital signatures and digital certificates in a nutshell. I hope that was useful, and I see you guys in the next recap video.